Hello everyone. So welcome to the 20th lecture of the course Discrete-time Markov chains and Poisson processes. So in the last module we saw about stationary distributions. I said that it is very important in the context of discrete-time Markov chains. Till now we have seen two important properties or two important results about stationary distributions. The first was if you start with a stationary distribution, that means if the initial distribution is the stationary distribution, then the distribution of all xn's is also same as the stationary distribution. So if you start from the stationary distribution, you remain there. That's one of the reasons why we call it a stationary distribution. Another thing we saw that if a Markov chain has or if an irreducible Markov chain has a stationary distribution, then all states are positive recurrent. Now the question is, are these all? So are these all about stationary distributions, or there are some other important properties of stationary distributions? The answer is yes, there is something more to stationary distributions, and that we are going to see in this module which we are going to start today, which is limiting distributions. Fine? Okay, so let's start. So first we start with some definitions. So for any state I in S, we define Vin to be like all t's between 0 and n such that xt is equal to I. Or in other words, it is summation k running from 0 to n delta I of xk. That means this delta I of xk is equal to 1 if xk is equal to I, 0 otherwise. So then what is this Vin? This is basically the number of visits to state I during 0, 1, 2 up to n. Remember, we have already seen this total number of visits where the summation was from k running from 0 to infinity, which we denoted by Vi, but now we are looking at Vin, which we are saying the total number of visits or the number of visits to state I during the time 0, 1 up to n, right, during the first n time units. Fine. Okay, that is the first definition. Now the second definition is, again for any I in the state space, define ln I to be Vin over n plus 1. But then what is this lin? So it is basic. So remember, Vin was the number of visits to state I during 0, 1, 2 up to n plus 1, but now we are dividing by n plus 1. So we are looking at the proportion. So this lin is called the empirical distribution at time n, or it is also, you can think of it as the proportion of times the chain is in state I, right, because the Vin is the total number of visits between 0, 1 up to n, and then I divide by the total time. So I get the proportion of times the chain is in state I. Fine. So that I call as lin, and this there is another name to it. It is also called the empirical distribution at time n. So if I look at this lin for all I in S. So if you fix an I, it is the proportion of times the chain is in state I, and lin is called the empirical distribution at time n, where now I runs from like I runs over the entire state space. Why it is distribution? Because you can easily check the way it is defined. If you do summation lin, say for example, if you do summation lin sum over I belonging to S, that will be equal to 1. This each li's are obviously greater than or equal to 0. So this is a probability vector, fine, or what is called a probability mass function. That way also you can think of it. So it is, that's why it's actually a distribution, and it is called the empirical distribution at time n. Fine. Now we come to the first theorem, which is called the law of large numbers for Markov chain. Now why am I calling it law of large numbers? Recall what is like what is law of large numbers. So for example, say if you are tossing a coin, then if I So, look at say the number of times you get I, or in other words, sorry, the number of times you get a head divided by n. So, if you look at that, or the proportion of times you get a head when you toss a coin n times. If I look at that, look at this quantity, then you know what law of large numbers tells you. It tells you that it goes to actually the probability of head of that particular coin, right. So, if I am looking at, like, if I am tossing a coin infinitely many times, and if I am looking at the quantity that the proportion of times the coin lands head in the first n tosses, then if I take n going to infinity, it converges to the probability of head. That is one implication of law of large numbers. So, you will see, so here I am calling this theorem as law of large numbers because it tells us the limit of this LIN, which is also the proportion of times the chain is in state I, right. Okay. So, let Xn be an irreducible and recurrent Markov chain. Fix a state I. Suppose that probability x0 equal to I is 1, or in other words, the initial distribution is delta I, fine. Then for any state j, if I look at this Ljn, that means what? This is the proportion of time. So, the chain is starting from I, and you are looking at the proportion of times the chain is in state j up to time n, fine. Then what this theorem is telling you, that this converges to gamma ij over EITI if EITI is less than infinity. And again, recall what is this gamma ij is what we saw in the previous module, that this is basically starting from I, the expected number of visits to state j up to the first passage time to I. That means you look at from 0 to Ti minus 1, where Ti is the first passage time to state I. So, that is gamma ij over EITI if EITI is less than infinity, and it is equal to 0 if EITI is equal to infinity. So, remember, it is a recurrent Markov chain. So, each state is recurrent, but now the question is whether each of them is null recurrent or positive recurrent. Remember, it is irreducible. So, either all states will be null recurrent or all states will be positive recurrent. So, if all of them are positive recurrent, then it converges to this quantity gamma ij over EITI, and if each of them is null recurrent, then it converges to 0. Again, see this each Ljn we have already seen, if you sum then it is equal to 1. Similarly, we also know that if you say sum gamma j I over all j, if you sum it over all j, you actually get EITI. That is from the definition of gamma ji, and we are dividing it by that. So, actually this quantity also, if you sum over all j, you actually get 1, right, because this sum over j gamma ji is EITI, we are dividing by the sum. So, now the total sum becomes 1, right. Okay. So, again this gamma ji over EITI is actually, so in at least in this case where EI of Ti is less than infinity, it is again a probability mass function or a distribution, fine. Okay, and now how is this like what kind of convergence is this? This happens with probability 1. Now, what is with probability 1? Remember this each Ljn, these are all random variables, right? Because so look at the definition. So, again it is a random variable. So, it for given each omega in the probability space, you will get one value. So, what this means is that for each omega, Ljn of omega converges to this quantity as n goes to infinity. So, this is convergence omega by so at each omega or for each omega. Again, it is not actually for each omega. What this with probability 1 tells you, like the set of all omega for which this convergence happens, that has probability 1. So, it is possible that this convergence fails for some omega, but the probability of the set of all omegas where this convergence does not happen, the probability of that set is equal to 0, fine. So, anyway, so the main thing is this is a random variable which it is telling you that for each omega this converges to this quantity, but remember this limit is actually a constant, but again a constant you can think of it again as a random variable. So, it says that for each omega ln j of omega converges to this constant if ei of ti is less than infinity and it converges to 0 if ei of ti is equal to infinity. Again it's although I am saying it for all omega, but again it's actually not for all omega. This statement with probability 1 means the set of all omega, so the set of all bad omegas where this convergence does not happen, that has probability 0. So, the set of all omegas for which this happens has probability 1, and in probability as long as something happens on a set with probability 1 we are happy. For all purposes it happens for all omega. That is why I am using it. Again it is not a very precise statement to say for all omega, but from a probabilistic point of view it is actually for all omega because it happens with probability 1. Fine. Now, in particular if I is positive recurrent, that means if ei of ti is less than infinity, fine. That means we are in this first case. Then if I look at ln I, now what is ln I? Ln I is now starting from I the proportion of time you spend in state I up to time n, but now that means, so this was for any j. Now if I take j equal to I, we know that gamma I is equal to 1. We have already seen this when we defined this gamma, this quantity gamma in the previous module. The first result we saw that there it was k, so it was gamma k is 1, but again here we instead of k we are taking the state I, so gamma I is equal to 1, and again it is very easy to see from the definition as well because this is the expected number of visits starting from I to state I up to the first passage time, but since that the first passage time is the first time after time 0 the chain hits I, so in between it will not hit I. So, the only time it is at I is at time 0. So, gamma I is equal to 1. So, now, so the numerator becomes 1. So, if I look at ln I, this converges to 1 over EITI. But now we know that this, if I is positive recurrent, we are in the setting of irreducible Markov chain. So, that means the whole chain is positive recurrent. Now, we know from the theorem that we saw in previous module that if you have an irreducible Markov chain and all states are positive recurrent, then there exists a unique stationary distribution pi I which is equal to EITI. So, what this theorem tells you that if you have an irreducible positive recurrent Markov chain, then this proportion of times the chain is in state I starting from I, this actually converges to the stationary distribution. So, you see in that way you get another important property of stationary distribution. So, again this is a very natural question to ask, that the proportion of time the chain spends or the chain visits the state I within first n visits, and it turns out that if the chain is irreducible and positive recurrent, then this quantity converges to the ith component. If we are looking at the ith state, then it converges to the ith component of the stationary distribution. So, you see stationary distribution here makes an appearance as the limit. The limit of what? The limit of the proportion of times the chain visits state I, right. So, since this is like as n goes to infinity, so this is also what is called the long run proportion of times. Long run because we are looking at n going to infinity. So, if a chain is irreducible and positive recurrent, and suppose you fix a state I and you say that the chain starts from state I, then the long run proportion of time the chain visits state I is equal to pi I. Long run proportion means the proportion as n goes to infinity. So, the long run proportion of time the chain visits state I or spends in the state I is pi of I, which is the stationary distribution. Fine. Okay. So, you see yet another important property of stationary distribution because it comes as a limit of this proportion of times the chain is in state I, or it is the long run proportion of times the chain is in state I. Fine. So, another important property of stationary distribution. It makes an appearance as a limit of something. Fine. Okay. Now, another important theorem. Okay. So, we have already seen that in a Markov chain, the states can be classified as either transient or recurrent. Now, if it is recurrent, then it can be further classified into two subclasses, positive recurrent and null recurrent. Fine. Now, so you fix a state I in S, then I is transient if and only if this thing is less than infinity. This we have already seen, and we have already seen a theorem which said that I is transient if and only if this quantity is less than infinity, and it is recurrent if and only if k running from 0 to infinity p I k is equal to infinity. In this case, it is recurrent. So, we have already seen this theorem. Fine. So, this first part is already proved, but now the question is, how do I know whether it is positive recurrent or null recurrent, right? So, I need some further criteria to understand this further subdivision, right? Now, this theorem talks about that further criteria. So, what this point 2 is saying, I is null recurrent if and only if this is equal to infinity. Anyway, this is fine because null recurrent means it is recurrent. So, if and so this thing has to happen, that this sum should be equal to infinity, and if you look at this quantity, limit n going to infinity 1 over n plus 1 k running from 0 to n p I k, that should be equal to 0, and I is positive recurrent if and only if, again this part is already done and this thing is strictly greater than 0. So, this quantity basically gives you the distinguishing criteria. The first is true for recurrence. Now, it is null recurrent if this quantity is equal to 0, and it is positive recurrent if this quantity is strictly greater than 0. So, this is one way of checking whether a state is positive recurrent or null recurrent, right. So, first, in order to check whether it is transient or recurrent, you need to check this quantity whether this is equal to infinity or less than infinity. Now, once you get, so if it is less than infinity, settle it is transient. If it is equal to infinity, then you have to further check whether it is positive recurrent or null recurrent. In order to do that, you have to look at this quantity. Fine. So, if it is equal to 0, then it is null recurrent, and if it is positive, if this limit is greater than 0, then it is positive recurrent. Fine. So, that is what this theorem tells you. So, now it gives you criteria for checking all three: transient, recurrent, null recurrent, positive recurrent. Fine. Okay. Now, let us look at the proof of this. The proof is more or less simple. So, here you see that I haven't assumed anything about the Markov chain, that whether it has irreducible or not, how many communicating classes it has, but so it is true in general no matter how many classes it has. So, for each state if you do all this checking, then you can say whether it is null recurrent, positive recurrent or transient. So, in addition, if you know that it is irreducible, then you just need to check for any particular state, then all states are same because all these are class properties. But in the proof, we will just assume irreducibility because that makes the proof little bit simpler, but the result does not need irreducibility. Fine, but for the proof, we will just assume irreducibility, that because under this assumption the proof is simpler. So, we will do proof. Okay. Now, before going to that, now let us see. So, it says that these are if and only if, but see, if we just prove that I is null recurrent implies this is true and I is positive recurrent implies this is true, then also we get an if and only if criteria. Why? Because say suppose we have shown that I is null recurrent if this is equal to infinity, as if this quantity is equal to infinity and this is equal to 0, and positive recurrent if this quantity is equal to infinity and this quantity is strictly greater than 0. Now, for the other side, so suppose we want to show that this plus this implies that it is null recurrent. Now, Suppose if it is not null recurrent, so again as soon as we know that it is equal to infinity, we know that it is recurrent. Now suppose it is not null recurrent, but it is positive recurrent, but in 3 if we have already shown that positive recurrent implies that this quantity has to be strictly greater than 0, then we will get a contradiction, right. So suppose we start from this. Now the claim is it has to be null recurrent. If not null recurrent, other option is positive recurrent, but if we have already shown that positive recurrence means this quantity has to be strictly greater than 0, but we started with that this is equal to 0, so it cannot be positive recurrent, but has to be null recurrent. So if we show this 2 and 3 only one side, because it's a dichotomy, a state can either be positive recurrent or null recurrent. So in order to show if and only if we just show one side of both these statements, that's enough. Fine. Okay. So we prove 2 and 3 together. So suppose we first look at, suppose I is null recurrent, right. Now as I is recurrent, this is equal to infinity. We have already seen this in a previous theorem. Now by previous theorem, the previous theorem I mean this one. So it says that ln I, if say for example if I look at for j equal to I, ln I converges to 0 if ei of ti is less than infinity, or in other words if I is null recurrent, right. So limit n going to infinity, ln of I equal to 0. Now I take expectation on both sides. So that will imply this, but here I have done a small thing. So here there is a small subtlety. I will not get too much into the detail of that subtlety, but I just want to mention. So say if I take expectation here, now expectation of 0 is 0, no problem, but you see in this statement what I have done is I have now pushed the expectation inside the limit. Now the subtlety is that you can do it in this case. Why you can do it in this case, I will not go into the detail of that, but I just wanted to point out that I have actually done that, and here it is actually, so there is no issue in doing this. So generally you need to, whenever you are pushing expectation inside the limit or summation inside the limit, you need to be careful whether you can do it or not, but in this particular case we can do that. Why we can do that? So that is because of some theorem, but I do not want to go into the details of that theorem. So here I have pushed the expectation inside the limit. So this implies that limit n going to infinity ei of lin equal to 0. But again, what was lin? Lin was 1 over n plus 1 summation k running from 0 to n del I of xk, right. Now again expectation of this is a finite sum, so I can actually push the expectation inside, but now this del I of xk, these are all random variables. What kind of a random variable? It is a very simple random variable, it is a Bernoulli random variable. So this is equal to 1 if xk is equal to I, 0 otherwise, right. So it takes two values, 1 and 0. So again, that is why I call it a Bernoulli random variable. So what is the expectation of a Bernoulli random variable? It is just probability that the random variable takes value 1. So here it takes value 1 when xk is equal to I. So expectation of, so what I am saying is that if I look at ei of, so I am doing here ei, right. So ei of del I of xk, that is nothing but pi of xk is equal to I, because that is precisely when it takes the value 1, but what is pi of xk equal to I? That is nothing but pii k, right. So that is why, and again this n plus 1 will remain as it is. So this is, so expectation of this is actually equal to this, but now you already know that this expectation is 0, so that implies limit n going to infinity is equal to 0. Fine. So we get this from that theorem which we started with in today's lecture, that lin goes to 0 if I is null recurrent. Fine. So then I take expectation on both sides of that and we get the result. Now suppose that I is positive recurrent. So, if I is positive, so for null recurrent we have shown that this has to be 0. Now, suppose that I is positive recurrent, again as I is recurrent this thing is true. Again by previous theorem we know that in this, so if I is positive recurrent then it converges to 1 over EITI. Again I take expectation on both sides, again expectation can be pushed inside the limit. So, remember this is a constant, so expectation of a constant is just that. So, limit n going to infinity ei of lin is equal to this, but now as I explained just in this case this expectation is equal to this. So, what this tells you is that limit n going to infinity 1 over n plus 1 k running from 0 to n piik is equal to 1 over eiti, but since I is positive recurrent we know that ei of ti is actually less than infinity, right. So, we know that since I is positive recurrent we know that ei of ti is less than infinity. So, 1 over eiti has to be strictly greater than 0. So, if I is positive recurrent we have shown that this is strictly greater than 0. Now, this also says that all these things are if and only because of the reason which I explained before starting the proof, that since now if I have to show that this plus this implies that it is null recurrent. Now, since this is equal to infinity we know that this is recurrent. Now, we have this. Now, if it is positive recurrent, now this part tells you that this has to be positive, but we are starting with that this is equal to 0. So, it cannot be positive recurrent, but has to be null recurrent, and similarly you can conclude for positive recurrent. So, these are if and only if criteria. So, this gives you a complete characterization of a state. So, if sum over k running from 0 to infinity piik is less than infinity, then it is transient. If it is equal to infinity, then it is recurrent. But what kind of recurrent, positive or null? For that we need to look at limit n going to infinity 1 over n plus 1 k running from 0 to n piik, and if this limit is equal to 0 then it is null recurrent, and if this limit is positive then it is positive recurrent. Fine? Okay. So, we will stop this lecture here. Thank you all.